Today we're learning about similar polygons. We have already learned about congruent polygons. The symbol for congruent being this one. These two Shanley shields are congruent. And congruent means same shape, same size. All the angles match, all the lengths match. But today is similar polygons, so there's actually a definition for similar. But you already have a good idea about what similar means just by looks. Which of those other two Shanley shields looks right to you? I would say that small one, right? Because it's resized correctly. This one's kind of all squishy, right? So we would say that last one is not similar to the other ones. But we would say that these two are similar. They're not the same size, but they are the same shape. So what symbol do we use for similar? It's one of these squiggles. What does the 2 squiggle mean? That means approximately equal to. Like when we say pi is about 3.14. So that leaves us with a single squiggle, and a single squiggle does mean similar. We would say that this one and this one are similar Shanley shields because the resizing looks correct. You guys have done this before where you resize an image, and if you pull on one direction, it's going to not resize it the way that you were hoping. Where if you pull on the corner, everything stays sort of in the position it's supposed to be in. That's similar. Now the geometric definition of similar has 2 things involved. Number 1, all the angles have to be congruent. For example, if you look on this angle of the Shanley shield up here, on the similar version of the Shanley shield, that angle up in the corner would be the same size. All the angles have to be congruent. Where if we look at this non-similar one, do you see how that angle has shrunk in? Not a congruent angle, so that doesn't count to be similar. But that's not all. Not only do we have to have congruent angles, we have to have proportional sides. We know that the sides aren't going to be the same length, but they do have to be proportional to one another, and that's why we've been studying proportions so much. So here's a couple of similar polygons. I can tell because it's using that little similar symbol right there. ABCD is similar to EFGH. And just like congruent statements, similarity statements have to be in the correct order. So see how the A and the E both come first? That means that angle A is congruent to angle E. And all of the corresponding angles must be congruent because these are similar polygons. That's the first part of the definition of similar. Now, like I said, these aren't congruent polygons. We aren't going to be able to go tick, tick on those 2 sides because they're not the same length. But the whole thing about proportional is we're going to be comparing the ratio of the length of AB to the length of EF. And if you were to look at that ratio compared to the ratio of BC to FG, and the other 2 pairs, all 4 of those ratios, if they are proportional, all 4 of those ratios would be equal to each other. And so that is the second part of the definition of similar polygons, that the sides are proportional. Say it with me. Congruent angles, proportional sides. One more time. Congruent angles, proportional sides. Here we've got 2 triangles. They kind of look like they're just resized versions of each other. So we are going to try to show that those are similar triangles. What does it mean to be similar triangles? Congruent angles and proportional sides. And I already see a bunch of congruent angles. Let's write them down. We have all 3 sets of corresponding angles congruent. Now we're going to want to check for proportional sides. Now here's a little trick I like to use. These are lined up pretty nicely, so it's pretty clear that the 10 goes with the 8 and the 15 goes with the 12. But sometimes they'll play tricks on you and rotate one of them, so it makes it a little harder. So I like to take the shortest side on the first triangle and compare it to the shortest side on the second triangle. and then the longest side on the first triangle and the longest side on the second, and then the mediumest one to the medium one. And what we need to check to see if these are actually similar is to see if all three of those ratios are equal, to see if they are proportional. And there's a few ways to do that. We could cross multiply and make sure that that comes out equal. We could reduce each fraction and see if they're all equal. And another way is we could just straight up divide 10 divided by 8, 20 divided by 16, 15 divided by 12. If those all come out to the same decimal, then they're equal to each other. I'm going to try that reducing thing. This first one I can divide by 2. Here I can divide by 4. Here I can divide by 3. Great news, friends. All three of those ratios are the same, so we can say that the sides are proportional. And we even know that the scale is 5 to 4. 5 divided by 4 is 1.25, so we could also say that the scale factor is 1.25, or if you'd rather leave that as a fraction, you could say that the scale factor is 5/4. Let's try writing a similarity statement, just like a congruent statement, only we'll use the similar symbol in between. And I kind of already have this lined up nicely with my angles, because I know that R matches with T, so I might just use that as my guide. The R goes with the T, the Q goes with the U, and the P goes with the S, and that should work out. The similarity statement. And then statement of proportionality. We sort of already did that when we were checking those proportional side lengths. But for the official statement of proportionality, we're going to write the actual names of the sides. The length of RP is to the length of TS, as the length of RQ is to the length of TU. And what's my last one? That bottom one, right? If we call that first one PQ, the ratio of PQ to SU should be equal to those other ones. So that would be called a statement of proportionality. Let's just practice a couple more. Do these look like well resized triangles? And how about these rectangles? Do those look resized appropriately? There's two things we need to check. We need to check congruent angles and proportional sides. Let's check congruent angles first. On the triangles, I am seeing swoops everywhere, right? X is congruent to D, Y is congruent to E, angle Z is congruent to angle F. So I do have congruent angles. Check. Do I have proportional sides? That's what I'm going to need to really check. And again, I like to go smallest to smallest, biggest to biggest, and medium to medium. And in this case, I went A to B, A to B, A to B. That's important. And are those equal to each other? Again, I could cross multiply if I knew what 6 times 18 and 12 times 9 were. Hopefully they're equal to each other. Or I could literally divide on my calculator. 6 divided by 9, 12 divided by 18. But when you can reduce, I think that's probably your best bet. 6/9 is the same thing as 2/3. 12/18 divided by 6 would be 2/3. And 8/12 divided by 4 divided by 4, 2/3. Looking good. And so what I just found out is that those sides are proportional. So are those triangles similar? Yes, they are. And what would my similarity statement be? If I call the first one triangle X, Y, Z, similar to, be careful, it's easy to get a congruent symbol in there accidentally. And the X goes with the D, and the Y goes with the E, and the Z goes with the F. And what is our scale factor? Your scale factor naturally pops out when you reduce those fractions. So do you see all those 2/3? Be careful though. Did you see they're asking me for the scale factor B to A? That's the big one to the little one. So it's not 2 to 3, it's actually 3 to 2. Kind of tricky. All right, let's check out those rectangles. Let's check our angles first. Do we have, yeah, they're all right angles. So we have all congruent corresponding angles, looking good. Since this is a rectangle, I know that this is also 12 and that's a 9, and this is a 10 and that's a 6. So let's see if those sides are proportional. If I take the smallest length from the first rectangle and compare it to the smallest length from the second, and then the longest to the longest. And normally I'd have to do 2 more, but since they all match, I'll just take care of those 2. Now cross multiply, divide, or reduce, your choice. I think I'll reduce again. This is 3 over 2, and this is 6 over 5. 3 times 5 doesn't equal 6 times 2. 9 times 10 doesn't equal 6 times 12. That just tells me that those sides are not proportional. So even though they're still rectangles, one of those is a squished up version of the other. They are not similar. And if they are not similar, we will not write a similarity statement and we will not have a scale factor. Check this out. It tells me that these 2 triangles are similar to each other, and they're going to have me find the value of x. Well, x is a side. I know the angles are congruent, but the sides are proportional, right? So I know that that 10 must match with the 15 in the same way that the 8 matches with the 12, in the same way that the x matches with the 9. Now, how do you solve for x when there's 2 equal signs? The answer is you ditch one of them. So we could either compare the 10/15ths to the x over 9 or the 8 over 12 to the x over 9. And that's just a simple little proportion that we're solving. A little cross multiplying should do it. 8 times 9, x times 12. Remember that we set those equal to each other. 8 times 9 is set equal to x times 12. And I find out that x equals 6, which looks about right in the picture, doesn't it? Could also plop it back up in here. 6/9 is 6/9 equal to 8/12 and 10/15. I think they are all 2/3, so that should work out nicely. Here we've got a rectangular pool and a rectangular patio that goes around the edge, and it's asking us to find the ratio of the length of the patio to the length of the pool. I'm going to go with length as the longer one, so the length of the patio is 48, and the length of the pool is 32. And so since those are both in feet, I don't have to worry about any conversions, but I should simplify that. Those both divisible by 16, I think, yeah. So it's a 3:2 ratio. The next one is talking about perimeter. Perimeter is just where we add up the 4 sides, right? We've got these nice rectangles. So the perimeter of the patio would just be the 24 plus the 48 plus the 24 plus the 48. Perimeter of the patio comes out to 144. And I saw my mistake on the pool. The perimeter of the pool, we're going to add up 32 plus 16 plus 32 plus 16, and that is 96 feet. And so for part B, I want to find the ratio of the perimeter of the patio to the perimeter of the pool, both in feet. And now I'll just try to reduce that. Could divide them both by 12. 96 divided by 12 is 8. Could go a little further. Divide by 4. 3 and 2. 3:2. Did you guys happen to notice? This just amazes me that these 2 ratios are the same. That's actually a good thing to know. I could have skipped all of that perimeter work had I known that in the beginning, that the ratio of lengths would be the same as ratio of perimeters. And doesn't that sort of make sense since perimeters are just lengths? That's kind of neat. Not only is it kind of neat, it's a theorem. Theorem 6.1 says the perimeters of similar polygons. If 2 polygons are similar, then the ratio of their perimeters is the same as the ratio of their side lengths. Good to know. That means all I'd really have to know is like one side length and one side length. And if they told me the perimeter of this one was, let's say 25, I'd be able to find the perimeter of this one, even though I don't know any of those other side lengths. Because 5 is to 8, as 25 is to the perimeter of the big one. Could cross multiply, but I'm seeing this little relationship. 5 times 5 would be 25. So 8 times 5 gives me that perimeter. The perimeter of the big one would be 40. One more little thing, it almost could be a theorem, but it says if two polygons are similar, any two corresponding lengths in the polygons are proportional to the side lengths. Here's what that means. If these two triangles were similar, let's make up some numbers. Maybe if this were a 7 and this were a 14. Can you guys see what the scale factor is already? It's a times 2, isn't it? And if this side were a 3, then this side would be a 6. I'm just making up numbers here. Maybe on this other triangle, if that were a 9, then on the big one it would be an 18, because we were talking about a scale factor of 2. Now here's where that key concept comes in. Remember the altitude where you drop a watermelon straight from the peak of the mountain? That altitude, let's say we knew that this altitude was 2.5. What this concept is saying is that this altitude compared to the other altitude would have the same ratio as all of those side lengths. Those altitude lengths are proportional to the side lengths. They follow the same scale factor, so 2.5 times 2, that would give us an altitude of 5 over here. So it's not only the side lengths that are proportional, but really any corresponding lengths. And that's our intro to similar polygons. 2 things to remember: congruent angles, proportional sides. Say it. Congruent angles, proportional sides. Very nice.